Every year we always buy them like one big gift, and the trampoline was just perfect. I think so. But anyway, shut up. All right. As of today, we have 7 class periods until your midterm examination. So excited. I got 2 days this week, 3 days next week, 2 days the week after. Although you guys know you have Monday the 18th off, right? Martin Luther King Day. Although for some reason... Why? It happens every 4 years. You know what's a better idea? Federal holiday on election day. That's a better idea. Oh, sorry. A better idea rather than the inauguration is having a federal holiday on election day. That's a better idea. Inauguration, not as important as the actual election. Okay, you could either watch it on TV or skip school. All right, just saying, giving you your options. Anyway, Martin Luther King Day, you guys have off. Although for some reason I think the teachers still have to come in. That's odd. And then the week after, starting Monday the 25th, are your midterm examinations. Excitement fills the air. It does. Given that, there are still a few concepts that I have to go over with you. In regards to this new chapter that we've been covering from before break. Before break, I had you guys on that Monday. The Monday before break, you guys took your benchmark, correct? Okay, cool. And then that Wednesday before break, I still taught a lesson. I'm going to be building upon that lesson a little bit today, of course, but we'll see what happens as time goes on. So here's what I'm going to need from you. In order to get this thing moving, in order to get this thing started, I'm going to need those notebooks. If you do not already have them out, I'm going to need them out and open. Let's see. That's what I need. Oh. Come on, you. No, not this one. Yeah, this one. There you are. I need that one. Are you guys familiar with the Lego Mario sets that just came out this year? You know what I'm talking about?
They're sold out everywhere.
We ordered it soon enough for my son. My son got the starter kit. Do you know what I'm talking about? I can't tell if he's being serious or not because he just turned and shook his head. Yeah, they are. Yeah. We bought my son the starter pack. And then from other people, from his grandparents, he got Bowser's Castle, which is like $100. And he got a few other like mini kits here and there. But he's got like this giant box full of like Lego Mario stuff that he can set up into a Mario level. And then actually play it with like the... Yeah. Yeah. We ordered it online. It got shipped. So it's like they were sold out at the Target over here. You build the sets, but then you can arrange the level however which way you want, And it's a very creative kind of system that they got going on there. He could spend hours doing that stuff. It's pretty awesome. I digress. So let's see what we got here. Chappelle. Oh, wait, so you work at Walmart, though? All right. Obviously, none of you were alive to remember this, but I'm sure you may have heard stories. Back in the mid to late 90s, there was such a craze on certain types of toys. There was one year when I was in like middle school where like Tickle Me Elmo was the biggest toy on the planet. And there were people literally like punching each other out in the store. I know. It was sick. It's like that's what people did on Black Fridays. Back in the day, we didn't have the internet for like Cyber Monday. They just had the Black Friday. So Black Friday, people died. Like they did. They were trampled. She's laughing at people dying.
Sorry.
Anyway, back to math. Let's call this inverses. Today is the 5th. Don't write a 20, write a 21. Although I've been writing the 21 with no problem, simply because, you know, it feels better. Anyway, all of today is based on the concept of inverses. To invert. I am going to put 2 equations. My paper moved. I am going to put 2 equations into my calculator right here. I just got to reset it. I'm going to put 2x minus 3. And I'm going to put parentheses 1/2 x plus parentheses 3 divided by 2. Now, I'll put these into my notes. Oh, come on. Have you guys had that issue too, where you try to backspace, it deletes everything? I hate that. X plus parentheses 3 divided by 2. Parentheses. Okay. I'll write those into my notes in a little bit, but the first thing I want you to do is to look at this. Look at what happens when I graph this sucker. Yes, obviously there are 2 distinct lines. The first one being the blue 2x minus 3, and the second one, the red one, being the 1/2 x plus 3 over 2. But there's something interesting about the way that this looks. Oh, hey, there's people there. Hi, peoples, in my chat. But there's something interesting about the way that these 2 lines look. Have you guys ever seen those videos online where it's like somebody makes like a reaction video where it's like, oh, that's so satisfying, or some junk like that? You see like that's like a candle getting crushed and then like a bunch of stuff comes out. It's like, oh, that, you know, people like it because it's like, oh yeah, that kind of is a little satisfying. The fact that it's like everything just kind of like goes at the same time, everything kind of looks a certain way, and it looks appealing to the human mind. There is something appealing about this graph, about these 2 straight lines. There's something appealing about it. My question to you is, what do you think it is? There's something about this image that just looks right. Ignore the colors. Don't worry about red and blue. But there's something about it that looks nice. Any guesses? Yeah?
Well, the point is 3, but it almost looks like it's the same. Like it's the same. Not graph, but like they look the same, but one's inverted.
But how? I agree. Yeah, they do cross each other at like an ordered pair. Don't worry about that ordered pair. But like I see what you're trying to say. Okay, yeah, okay, so like wherever this point of intersection is, it's like the point of intersection, the distance to the x-axis and the distance to the y-axis look exactly the same. Yeah, I agree. Now, you mentioned something about being inverted. I'm thinking back to a geometry concept. Again, not to PTSD you guys with geometry. But I'm thinking back to a geometry concept. There's something about these 2 lines that you could describe using a geometry terminology. Let's say. Say again? Reflection. They're reflections of one another. They are. They're definitely reflections of one another. And more specifically, they're reflections across what? Not the x-axis. Not the y-axis. No, you wouldn't be reflected across a point. Well, she said x-axis, you said y-axis. And I said no. When you guys did reflections in geometry, did you do it with like on paper where you would like fold stuff in half? Yeah, kind of like that. It's being reflected. I agree with you. It is being reflected. But what is it being reflected across? Well, I got to type in a third equation. Chapow! It's being reflected across that diagonal. The diagonal y equals x. The idea of inverses goes a lot deeper than this image that you see in front of you. It goes a lot deeper. When you think of the word inverses or inverse or invert or inverted, what type of real life example do you kind of think of? What do you mean? It's like reflected. Yeah. Or mirror images. I agree. Why? That's true. As a complete side note, unrelated to everything that we're doing here. No, exactly. Yes. I agree wholeheartedly, and I'm going to get into that. I will. But you're talking about like not looking the way you think you look. Have you ever done an experiment? You could do this on your own. You take a picture straight on of your whole face. You go into Microsoft Paint. You cut half of it off and then reflect it over. So you get like 2 right-sided faces and 2 left-sided faces, and then you realize my face is not symmetric. Yeah, you should try it. It's pretty fun.
I think I saw that, but I saw someone do it when they had not a perfect symmetrical face, but like it was like really close.
Mm-hmm.
There was like some
slight variations, yeah. But that's the thing.
Like other than that, like they didn't look that different. Like the face looked like a little skinnier or something like that, like wider.
The interesting thing is human beings naturally are attracted to symmetry. You know what I'm saying? You're laughing, but
Actually,
yeah.
I read something that said that like scientists said that like a certain like over 50% of people find symmetrical faces attractive.
All right.
So maybe you're wrong, maybe you're right.
Okay. All right, back to this. So let me talk a little bit more about these 2 equations. I'm going to say, now these 2 equations, y equals 2x minus 3 and y equals 1/2 x plus 3 over 2. These 2 functions are inverses of each other. Now, there's a lot of reasons. There's actually 3 specific reasons why that is. One of the reasons is the visual graph that I just showed you. Give me a number. Give me any number. 4. Okay, check this out. Plug the number 4 into that first equation for x. What do you get back? Cricket. Plug 4 to that first equation for x. What do you get back? You get 5. Cool. 4, 5. Good for us. We did it. Yay! All right, that's not what I wanted to show you. Check this out now. Y equals 1/2 x plus 3 over 2. Plug a 5 in for x. First of all, what's 5 times 1/2? What's 5 times 1/2? You can do it in your head. What's half of 5? 2.5 plus 1.5. What is 2.5 plus 1.5? 4. What do you notice about the ordered pairs? They're what? They're inverses of each other. Give me another number, any number. 12. All right. 12, parentheses. 12 times 2 is 24. 24 minus 3 is 21. But then if I plug in a 21 here into the other equation, if I plug a 21 in right here, 21 times 1/2 should give me 10.5. 10.5 plus 1.5. What do you get? 12. They are reflections of one another. They are inverses of one another. They are symmetric to one another. Not only visually are you able to identify that the graphs look like reflections of one another, but on a computational level, every single ordered pair is now a reflection of one another in the other equation. There are 3 specific reasons why these 2 equations are inverses of each other. 3 specific reasons that I want to get into on the next page. Hold on here. Hold on here. Hold on here. On the next page, here's a definition for you. If f of x and g of x are inverses, then ... If f of x and g of x are inverses, they invert each other, then there are actually 3 definitions that I need you to write down. First, their graphs reflect over the line y equals x. Their graphs will reflect each other over the line y equals x. They invert each other. Another idea, another concept of the word invert means to undo what you did. It's a very strange thing to say, to undo what you did. If I walk 3 steps forward, how do I invert myself? Yeah. I start out where I started, or I finish where I started. I undo what I did. It's very strange to think of inversions like that. Second bullet point. Every ordered pair x comma y in f of x becomes y comma x in g of x. Zoom in on that statement. Every ordered pair x comma y in f of x becomes y comma x in g of x. They are inversions of each other, inverses of each other, I should say. There is one more bullet point that is also very important, which is going to lead us into the next part that I want to talk about. And it has to do with the composition function. Now, the composition function is something that we talked about before we left for break. It's what we talked about on that Wednesday before break. The composition function is the act of putting one equation inside of another equation and then simplifying it down. The composition function can become very handy, especially when you're trying to do multiple steps within an equation or computation. But if f of x and g of x are indeed inverses of each other, then when you take the composition, it should simplify to just become an x and nothing but an x. The 2 functions basically cancel each other out, and you're left with nothing but x. That is what it means to be inverses of each other. So, for example, give me a number, any number. 7. If you plugged a 7, you would get a 7 back, meaning nothing happened. Oh, but f of x is supposed to do something. I know. And then g of x is supposed to do something. I know. Basically, they canceled each other out. They inverted each other. It told you to take 3 steps forward. Well, the other function told you to take 3 steps back. You ended up back where you started. Every ordered pair, x comma y becomes y comma x. The graphs are reflections of one another over the line y equals x. So here's what I got for you. I have a worksheet that I am going to pass out to you. For those of you that are in the online video or this live stream right now, I'm going to be posting this worksheet to the Google Classroom stream in a couple minutes. Give me one moment. Let's do this. There's 3 there for you to pass one back. There's 3 there. And then Google Classroom, this class, add from the Google Drive. Come on, there you are. Insert PDFs for today. Post. Chapow. There we go. Excellent. So for those of you that are in the live stream, I just posted the PDFs of the worksheets that I'm talking about into the Google stream. You can see them there. The one that I am more interested in, the one that I am focused on for the time being, please make sure that you are on the 6.2 side of that worksheet. 6.2, 6-2 side of that worksheet. And I'm going to bring that up on the screen in a moment. So on the 6.2 side of that worksheet, click, zooming in. Let's just start by looking at numbers 1 through 6. What I'm about to show you is quite possibly the easiest thing that you will do all year. Let me repeat that. Numbers 1 through 6 are quite possibly the easiest thing that you would have ever seen in this entire school year. Numbers 1 through 6, the directions are asking for you to find the inverse of each relation. How many ordered pairs do they give you in number 1? How many ordered pairs do they give you in number 1? 3. What's the inverse of 0, 3? It can't be that easy. What about this one? That's ridiculous. What about this one? That has to be some kind of a catch. What? OMG. No, there's no catch. There's no catch. That's it. That's literally it for that problem. You're like, oh, give me the test now. Okay. No, I'm not going to do that whatsoever. But no, literally, that is what you're supposed to do for that problem. 3, 0, 2, 4, -6, 5. Boom. That's all you have to do for that problem. There's nothing else to do for that problem. It's the same procedure for numbers 1 through 6. The exact same procedure. Done and done and done and done. All right. Cool. But yeah, that's literally all you have to do. Let's look down at number 7 then. Let's look down at something that's a bit more interesting. I'm looking down at number 7. Find the inverse of each function and then graph the function and its inverse. Now, I'm going to actually bypass finding the inverse first, and I'm going to actually graph it. I know I mentioned geometry giving you PTSD. Does the same thing happen when I say algebra 1? It shouldn't as much. Not as much, right? You guys remember how to graph lines, right? I would hope so. Number 7. It's a linear function. They want you to graph it. All right. Y-intercept, up 3 over 4. I'm going to go the other direction as well, over 4. I'm going to draw that line. Yeah, I nailed it. So now here's the deal. I have to graph the inverse. What I know about the inverse is that every ordered pair, x comma y, is supposed to become y comma x. What is this ordered pair right here? What is the value of this ordered pair that I'm pointing to? 4 comma 3. Which means in the inverse, 3 comma 4. It can't be that easy. Yes, it can be that easy. Look what I'm doing. I'm putting it in purple. I'm putting it in purple so you can see it a little bit better. Isn't purple more appealing than blue? Okay, nobody agrees with me.
Yes, I agree. Actually, no, I don't agree.
You just raised my heart and then you dashed it. Anyway, what's this ordered pair right here? And what would be the inverse? Yeah, I know. There's no real fun there, but whatever. Cool. I'm just going to fill that in. And then logically, this one down here is -4, -3, which means -3, -4. I'm going to draw that line. But, whoa! Sounds like opera. But that's my inverse. What is the equation of that inverse? It's got the same y-intercept. They don't always have the same y-intercept, but what's the equation? Yeah. I'm going to call it g of x for now. I'm going to call it g of x for now. I'm going to give a different notation later. But yeah, it's 4/3x plus 0. They don't always come that easy, though. They don't. They do not always go that easy. But that is the inverse. What I drew in purple is the inverse function. It follows all of the rules that we've talked about. Here's what I want you to do. I want you to take a few minutes, and I want you to knock out number 9. On number 9, they give you the function y equals 3x minus 2. I want you to graph it, and then I want you to find its inverse graph, and then try to take a guess as to what the equation of the inverse would be. Let's take a few minutes. Let's knock out number 9, and let's just see what happens. just going to plot the line here. Where I go up 3, 1, 2, 3 over 1, 1, 2, 3 over 1, go backwards 1, 2, 3 over 1, and draw my little line out. That's a terrible straight line. Thankfully, I have the ordered pairs there to kind of fix it. See, you draw that a little better. Hold on. That's no better. Okay. Where's my purple? My purple colored pencil. All right. Ordered pair here is 2, 1, 2, 3, 4. 2, 4 becomes 4, 2. 1, 1 becomes 1, 1. That doesn't change. 0, negative 2 becomes negative 2, 0. And negative 1, negative 1, 2, 3, 4, 5 becomes negative 5, negative 1. And then I can draw that sucker like that. There we go. Ah, that's a terrible line, but I'm still going to draw it anyway. That is my inverse. Anybody come up with an equation for it? Anyone come up with a slope for it? What is the slope of that inverted line? Oh no, crickets. 1 over 3. Any guesses as to what the y-intercept is? How about this? Better yet, why is the y-intercept not easily recognizable? Where does it cross? No, that's the original y-intercept. What about the one in purple? Yeah, that's the problem. It's a decimal. It's a fraction. Ah, if only there was an easier way. That's why I kind of enjoy infomercials a little bit. Here's what I'm referring to. What I need all of you to do, after you've drawn all that stuff, I need you to go back to your notebooks. So, let's go back to our notebooks. Let's see. Zoom out, zoom out, zoom out, zoom out, zoom out, zoom. There we go. So the example in question is number 9. Now, I am going to show you on paper how you can find the inverse equation. And then I'm going to write down your steps a little bit later on. So here's what you would actually do. Here are the procedures for finding the inverse equation. What the heck did I just do? Literally, what did I just do? Yeah. I mean, okay. But that makes sense in the context of inverses because every single ordered pair x comma y becomes y comma x. All right. I can deal with that. What do you think I'm trying to do next? What do you think I'm trying to do next? I'm following a couple of steps here. What did I just do next? Yeah, I got y by itself. There's the 1/3 x. There is the 1/3 x. There's the y-intercept. The one that we couldn't visually identify, but now you know exactly what it is on paper. This is the inverse equation. Now, there are a certain set of procedures that you would go through in order to get that. I'm going to write out what those procedures actually are. Let's zoom this up a little bit. There we go. To find the inverse equation. Step number 1. Now, there are a few steps here that are pretty self-explanatory, but I am taking this very carefully step by step so that you can see exactly what it is that you are supposed to do. To find the inverse equation, step number 1. Now, this is an if needed. If needed, change f of x to y. If needed, change f of x to y. You don't always have to do that. Sometimes they don't even give you f of x. Sometimes it's literally they just give it to you as a y, so you don't have to worry about it. But if needed, you should be changing that f of x to a y. Step 2. This is literally what we did before. I am going to switch x and y, literally switch their positions within the equation. That is the inversion step. That is inverting the two variables and thus changing what the equation actually is. Step 3, and you saw me do this, solve for y. Just get that y by itself. Step 4, again, this is an if needed situation. Change the y to the following notation. Now, I'm going to zoom in on that a little bit more. Help me out here. What the heck does that look like to you? And what position is that -1 in? Yes. It looks like it's an exponent. It looks like an exponent. Well, two things to that. Number 1, yes, technically it's in the exponent position, but no, it's not actually an exponent. What that means, what this means, and actually let me put this into my notes here so that we have the actual verbiage for this thing. The actual verbiage here, zoom out, there we go. That's how you would read it. You would read it f inverse of x. That -1 exponent, not really an exponent, actually is telling you to read the word inverse, f inverse of x. Strange, I know, but that's what they want. If you look at the worksheet that I gave you, look down at number 17. Look down at number 17, and you'll see that notation written for part A, where they say, find the inverse f -1 of x. That's really read f inverse of x. And like I said, the inverse is just nothing more than undoing what it did, taking the steps backwards. It's very strange, very odd, but that's what they want. Here's what I want you to try. I'm going to give you a couple of minutes to try this. Example. Here is the first equation that I gave you today. Here is the first equation that I gave you today. I want you to take a couple of minutes, and I want you to walk through those steps to find an inverse. I want you to follow all 4 of those steps and actually get the proper inverse equation. Take a few minutes, do that now. Let's see what the first step looks like. Step 1. If needed, change the f of x to a y. Again, that's not entirely necessary, but I like doing it. Step 2. Switch x and y. Okay. Literally switch their positions within the equation. Got it? Step 3. Solve for y. Well, it looks like if I'm going to solve for y, I'm going to have to add 3 first and then divide everything by 2. That means that I'd get y equals 1/2 x plus 3 over 2, which is the exact equation that I had at the beginning of this class period. And once again, if needed, and I like doing it, I like replacing the y with that proper notation of f inverse of x so that it can actually be seen as the proper inverse of x. It's kind of nice. Now, there were 3 bullet points that I gave you as the definition of inverses. 3 bullet points. Bullet point number 1. If f of x and g of x are inverses of each other, then their graphs should be reflections of each other over the line y equals x. We showed that. Number 2, bullet point 2. If f of x and g of x are inverses of each other, then every single ordered pair, x comma y, should become y comma x in the inverse. Yes, we showed that. What was the third bullet point? Ooh. What was the third bullet point? If they're inverses of each other, then what should be true? Ooh. Cricket, cricket. What is that function called? Let me write it out like this. I'm not giving it away just yet. In my notes, f of x equals 2x minus 3. G of x equals 1/2 x plus 3 over 2. If those two are inverses of each other, what is this called? What is this notation called? Say again? Well, that's all function notation. But what happens when I put one inside of the other? What do we usually call it? They're the type of notebooks that look like they have like black and white marble on it. Yeah, it's a composition function. Composition, you're composing the two functions together. If these two are inverses of each other, then what should the composition result in? What do our notes say for the third bullet point? Should be. If we don't get it, then something went wrong. Let's see what happens. Let's just see what happens. I want to perform the composition, meaning I have to put one equation inside of another equation. Well, the outer framework is this. This is the outer framework right here. That is my f of x. That's the outside. The f of x is supposed to perform 2x minus 3, 2 times whatever I'm inputting, minus 3. But instead of inputting a number, I'm going to input a function. I'm going to input an equation. But the equation that I'm inputting is 1/2 x plus 3 over 2. That's my g of x. That is going inside of the f of x function. Now I got to simplify. 2 times 1/2, cancel each other out. 2 times 3 over 2, because I got to distribute, just becomes a 3. This, oh, look at that. Equals x. That x, it has to be an x. It cannot be a negative x. It cannot be an x plus 1. It has to be an x. If you perform the composition and you get precisely an x, this verifies inverse functions. This verifies it. This confirms it. This proves that f of x and g of x are inverses of each other. Performing the correct composition operation and getting that x is vital if you have to prove or show that they are indeed what they say they are. Please keep that in mind. Now, there's a couple things I want to show you on this worksheet. Go back to the worksheet that I gave you. And let's look down at numbers 10 through 15. 10 through 15. Determine whether each pair of functions are inverse functions. And then write yes or no. Literally, okay, are they inverses of each other? I mean, number one, I could look at the graph, but the graph isn't always the best indicator. I could always look at the ordered pairs. However, I would have to check an infinite number of ordered pairs. Instead, I am going to perform the composition. F of g of x. I'd have you put this directly on that worksheet. F of g of x. The outside framework is the f of x function, which is x plus 6 or blank plus 6. And I am literally going to be inserting the g of x function inside of there. There's nothing to distribute. The 6's cancel, and I'm left with an x. What do I write for my answer for number 10? Yeah, I write a yes. Yes, they are inverses of each other because I just got an x. Yes, they are inverses of each other. Absolutely. Now, that doesn't always happen. That doesn't always happen. I could scoot over and look at number 12, and I could perform the same operation on number 12. G of h of x. G of h of x. Okay, well, g of x is the outside framework. That's 13 times the input minus 13. I plug in this function right here. I distribute the 13, and I get 1x minus 13 minus 13. What is negative 13 minus 13? What is negative 13 minus 13? Oh no, we forgot how to do math. This is where a lot of people get tripped up because they automatically think 0, but it's not. What is it in reality? Cricket, cricket. Oh, y'all killing me today. just for the sake of argument, because I do have one more thing to talk about. It's negative 26. This is a big no. They're not inverses of each other. They're not. They can't be. There is one more thing I have to talk about today. And it has to do with what's on here. Look at my screen. You ever see those dots in the top right corner? Do you know what they are? It's those dots show up when you paused it accidentally. I paused it on purpose. But you can actually pause when you're graphing something. I'll unpause it. Check this out. Chapow. Oh, I totally mistyped one thing. Hold on. There it is. Graph. These two functions are inverses of one another. Let me show you what I mean. This is a function that we have been dealing with since the beginning of the school year. This is your typical x squared function. This I love that noise. Is actually two different functions in one. It's plus or minus the square root of x. Do they appear to be reflections of one another across the diagonal? How about this? It might be a little easier to see it if I do this. They are. Think about the idea of inverses. I asked you the question, if I walk 3 steps forward, how do I invert myself? Okay, and I end up back where I started, right? I undo what I did. When you square something, what happens when you square root it? When you square something, what happens when you square root it? What happens to the square and the square root? Give me a number, any number. 13? If you took 13 and you squared it, you would get 169. What happens when you square root 169? You get 13. You end up right back where you started. You inverted it. A square root and a square cancel each other out. They cancel each other out. A square and a square root invert each other. These are inverted functions. These are inverse functions of each other. This is what the main focus of our next class period is going to be on, the concept of square root functions. We're going to be graphing them. We're going to be identifying properties on them. It's all leading up. I'm actually going to be assigning before the end of this marking period a project. I am going to be assigning a project because I like to do one per marking period. And we are going to do one on this concept of square root functions. Oh, we're going to get there. Anyway, that's it for me today. I'll see you guys again on Thursday. For you guys in the chat, I say bye-bye. I'm going to go home and jump on my trampoline.